So it's my privilege to introduce our first speaker for the afternoon session. William Brooks is an LRGF fellow. He's at Texas Tech University, works in the field of pulse power, and he did his residencies both at Sandia National Laboratories in New Mexico. Please take it away.
All right, so nobody's read my title, which means I have to read it for you, no matter how much I want to skip that. An experimental apparatus for direct observation of anode-initiated vacuum surface flashover. You can see a handful of my collaborators listed here. Both of my collaborators from Sandia National Labs are in the audience, which means I'm probably going to get some fun questions at the end. Now, for anyone who's not in this specialty, I'm sure that's a bunch of words that mean nothing to you, so let's get started with the presentation. Very brief introduction to pulse power. We've talked a lot about how it's applied, what you can do with it, and some of the experiments that have depended on it. But fundamentally, what is pulsed power? The idea is, in order to drive some of these advanced experiments and understanding of fundamental physics, you need to deliver a lot of energy very quickly. You can't just tap into a nuclear power generator or a nuclear reactor because it's not powerful enough. So you shrink your experiment in time, you deliver a little bit of energy really quickly, and all of a sudden you can hit a gigawatt without really trying. So we've seen this picture about a half dozen times. There's only a couple pictures with cross sections of the Z machine out there, and I think we all steal from the same two publications. The Z machine is a large-scale pulse power machine, which starts with 22 megajoules of stored energy in capacitors, and then it transitions it all along the radial axis inward until it's compressed both in space and in time. Unfortunately, each time you compress it, the constraints on how to push the power forward are a little more difficult, and ultimately getting the power from the capacitors into the load section is a difficult problem. Fundamentally, what we're going to be talking about is this nice, beautiful little line right here between the vacuum section and the water sections, which forms the transition from water into the midle stack. And it is along this beautiful little line here that we place a bunch of pieces of insulator, which have to hold off the entire load, the entire field being applied across an admittedly fairly large gap. And if you get breakdown across that particular region, your power doesn't get to your load, and the fun science that we want to do over here in the center, find my laser pointer, just doesn't happen. Or if it breaks down prematurely, the physics that we were expecting to initiate and then move on to driving something like inertial confinement fusion doesn't happen. So, how do we answer the fundamental question of getting the power there? And I think the question that appeals to a lot more of the physicists in the room: how do we get more power for more science? And so the answer is, we make the insulator better. This is one of the weakest spots in the pulse power chain, in that causing arcs across the surface between the anode and the cathode is much easier than causing bulk breakdown in oil or in vacuum or in water, which the other constituent components are made of. There are two fundamental types of surface flashover: cathode-initiated flashover, where an electron starts at the cathode and hops across, cascading as it does, liberating gas, and ultimately causing gaseous breakdown just above the surface. And unfortunately, that one was relatively easy to fix. Just keep the electrons from hopping across the surface. What does that take us to? Pull the electrons away in the background electric field. Problem solved. Well, no. We pushed into higher energy levels, and we end up at the anode-initiated surface flashover regime. Now, this is a point that's not well understood. A lot of the theories are best described as proposed mechanisms and not true theories with any kind of rigorous description. These are all my disclaimers ahead of time. But what we believe happens is we rip out electrons from the insulator, and along the way, we're knocking out gas molecules along the surface. Those gas molecules ionize, they conduct the electric potential from the anode into the cathode, or along the insulator towards the cathode, and what you end up with is a gap that starts closing itself. Unfortunately, the best way to prevent this problem is to stop it from happening and to avoid it occurring at all. And it's a runaway process, and that sets the limits for where your flashover occurs. In terms of a large-scale machine like Z, ideally you don't want this to occur during the forward-going pulse, and it really does set the limit for how much energy you can deliver at that section without either needing a much larger insulator stack or needing a faster pulse or a much better material. And so the question is, what are the underlying principles behind this? How do we understand it better? And fundamentally, how do we push that limit to allow for more energy and greater fields? We've already touched on a lot of the motivation. The idea is, despite being very pretty to look at, sparks are bad. That it represents energy not going to the science that all of us are so very passionate about. In terms of the stuff that we did here at Texas Tech University, we pioneered a pin plane geometry where we were trying to reduce this radial cross-section, which on Z is, I want to say, about 3 meters, to ideally a gap so small that we could look at it and point all of our diagnostics and measure it all at once. Spoilers, it's a very difficult task. We're going to show a lot of cases where it doesn't quite work the way you want. And no matter how hard you try, no matter how much the electric field stress is indeed the highest right in the center gap, the reality doesn't necessarily like to fit with our simplified models. So, touching on the scaling idea. Even in a small case, that is a huge circumference. Traditionally, you would make these out of a radial part, and that makes it very hard to diagnose. You can point a camera at maybe a small solid angle of that, but until you're leveraging 6, 7, 8 cameras, you're not guaranteed to capture it. So studying it becomes a statistical process, where you either get lucky and it happens where you want, or you have to field 6, 7, 8 times more diagnostics than you can afford, and diagnostics are expensive and hard to come by. So looking at some quick statistics, what we find out is we can in fact push some arcs across here, but by the time that the system was developed and devised, the measurements we were taking were for bipolar flashover, so the voltage would swing very positive and then swing very negative and then oscillate back and forth. And to the best of our understanding, this ended up biasing the insulators in such a way that the overall performance was significantly degraded relative to a unipolar configuration, which is what is technically relevant to a machine like Z or Saturn. In fact, if we compare the two, what we end up finding is the parameter is almost exactly half in terms of the characteristic model. A big part of the development of this project was getting it to break down where we wanted it to. So spurious flashovers, flashover anywhere but the point we designated in the center, and some quick lessons. Sharp corners are bad. Flat surfaces are bad. Designing your high voltage feed through incorrectly is bad. Even when you get all of that right, parallel surfaces at right angles to your electric field flash over much, much more preferentially to that insulator wedge. Getting your electricity into the system is hard. And this really underpins a very important detail, which is that when you are trying to cause breakdown in one specific location, the entire rest of the system must be far more robust than that one point. And as we studied this under virtually ideal conditions using pristine insulators that are some of the best characterized materials in published literature, everything else breaks. And we spent a lot of time troubleshooting that. So you do that, you hammer out some of the flaws, and what do you find? It's still kind of hard. The first few publications that we're able to produce required the inclusion of a piece of wire which represented an initiating flaw, something like a defect, a crack, or some other nucleating site for starting the breakdown process. And this is located at the anode, which is spherical here, and we can see the cathode base here. But fundamentally, if you add the wire and you stress it hard enough, and we're talking hundreds of kilovolts per centimeter, you can make a nice pretty arc across the bottom. Characteristically, in the description of anode-initiated flashover, what we're going to find is ideally we'd like to see some fractal-like tree growth, and then most of this structure is going to end up being etched into the top surface of the insulator, which is contrasted with cathode-initiated flashover, where you're not going to see much damage to the insulator in post. So this leads us to the desire to build a second generation machine, having found out that the machine that we had, which was about 10 inches by 10 inches by 10 inches, just wasn't going to get us where we wanted to be, and we wanted to scale higher so that we would have more application-relevant studies. And in that way, we ended up designing this beautiful vertical structure because our primary concern was ensuring that the only place that touched with any appreciable closeness was the insulator we wanted to arc across. And unfortunately, that meant the whole thing had to be a vertical stack up in order to accommodate mechanical constraints, which required us to build a platform around it, orient the entire thing upright, and then we seeded it with several diagnostics. Anode CVDs, capacitive voltage dividers. We experimentally tried a few BDOT configurations, but fundamentally we couldn't get the resolution in time and signal intensity that we wanted. And ultimately, we ended up leveraging a slow-wave Rogowski coil, which has a very limited recording length, but has excellent sensitivity and time resolution. Along the way, this is a development project where we refurbished the Marx generator and pretty much everything else is new construction. We did have some bumps along the road. There is an output switch gap, which is a coaxial structure right here, right in here, where basically you have this nice pretty donut which couples to another donut and you get arcs across it to get your output. Allows the rest of the machine to be isolated and safe to touch when you're not using it. A nice feature to keep, I might add. But if you do not operate the switch correctly, what you end up doing is blowing holes through it, arcing across the side, and permanently destroying the machine. We had to do a little bit of work in order to revise that. And ultimately, when we did the analysis and we looked at what we had, what we found is from purely an electrostatics perspective that that insulator was going to be under a lot of electric stress no matter how we operated it. And fundamentally, it was going to be at risk of being a flashover location or a source of arcing as we pushed to higher and higher regimes. Because again, these almost perfect samples are fantastic ways to find all the other locations on your system that break first, and inevitably do break first. But with a little hard work, you can make arcs in the right spot, mostly right spot. Getting all that together, we still had to do some troubleshooting, and we have a few options here. The first thing we see is we have this nice, beautiful divot in our data where it spikes about twice as deep, and it took us a couple months to figure out what was causing that. And in fact, the problem is because of where my ground terminal was located along the main current path, when the arc formed, a bunch of current avalanches across this region, and then the very small resistance presented by a piece of copper, or sorry, in this case, a piece of aluminum, shot up a few hundred volts and then coupled into the system. But ultimately, we diagnosed that by adding another voltage divider further in the system, finding out that they align almost perfectly up to the spike, and then comparing it to SPICE simulation, where we essentially have complete confidence that this is a result of spurious signal and not something being measured. The other big thing to consider is, pick my laser pointer, this point, this point, this point, this spike, in a perfect system should all be roughly at the same location. So we had to do timing analysis and timing compensation, especially for cable length, which though we went to a great length in order to keep the cables all exactly the same length, fundamentally we're still almost 40 nanoseconds adrift between various modifications and additions. This is an easy thing to correct for, but it is a problem that you have to deal with as an experimentalist. So, results, things that are interesting and things that we were able to accomplish in the course of our time at the fellowship. We did take a couple unipolar discharge shots, and we were able to, from the fine resolution in this particular image, be able to do some characterization of the arc plasma. So for purposes of description, we're going to define this nice red path from here to here and all the way down as the main channel path. And we estimated a bunch of dots, where the dots are roughly located at the roots of the branching centers. So the center-to-center distance between branching centers is about 264 micron at a standard deviation of about 128 micron. We characterized a secondary path, which is going to be this long runner, which streams all the way out to the side. And again, we get a similar number, 275 micron, at a standard deviation of 173. And then all the way near this tertiary branch, which happens just before we connect with the ground, we get about half that value at 130 micron with a standard deviation of 42. And we had enough resolution in this one particular image. We got very lucky with this one. I'm not going to pretend like we were able to focus this camera perfectly every single time. We were able to do some point-wise comparisons where we take a dot above and a dot below and be able to assess what the approximate diameter of the luminous channel is over a series of trials, and then we would average that out. And in that regard, the main path had a channel diameter of about 103 micron at a standard deviation of 18. The secondary path, which is going to be along, sorry, I can't find it in the photo, should be somewhere in here, was about 72.5 at a standard deviation of 15. And the last feature that we really noticed, which was very striking and very distinct, is we don't just have downward branching per se, but all along this top row, we have these cute little filaments that develop into a nice bulbous diffuse plasma. And mostly from eyeballing it, we had tried to assess what the approximate center-to-center distance is representative of that particular piece. And in that measurement, we found that it was about 130 microns center-to-center at a standard deviation of 42 microns, which surprisingly is fairly consistent given the method for which we use to assess this. A lot of the subsequent data, we had to allow this to oscillate back and forth. We found there was a fundamental limit imposed by the resistor that's in the system. We replaced the resistor with oil, and then the system became underdamped and it oscillates back and forth. We went to bipolar excitations. For purposes of diagnostic comparison, what we can see is the very noisy line in blue is the small oil CVD, which is physically very far from the diagnostics of interest. But we have a red and orange line, which are representative of the anode CVD, which is directly across the AK gap of the insulator we're testing, and the orange trace, which is the vacuum feed CVD, which is located physically 9-10 inches upstream of the diagnostic. All have fantastic agreement, and we're measuring out to, I can't make out that number, I'm going to call that 300 kV if I'm not reading correctly. I have poor eyesight, I apologize. And again, you do all of this and you make pretty arcs. The big difference is in this unipolar configuration, we noticed a very pronounced amount of diffuse plasma, whereas in the previous photo, you didn't see this massive glowing halo. That's not a consequence of whether we set the camera right, but in fact, something that we did observe when we allowed it to oscillate back and forth. We believe that that's a consequence of the reversal in terms of the potential of the anode and the cathode, where the cathode is held at plus or minus, and the anode is at ground potential. So relative to that gap, you see a swing plus minus several times. It's severely underdamped. We did get some unexpected results. You can't see it very strongly, but in general, the branching features that we see in anode-initiated flashover, and we have the voltage waveforms to confirm that this broke down on the negative voltage swing on the first pulse, doesn't have nearly as much developed fractal branching. We don't see as much outward growth. We don't see any kind of angel wings or trees, depending on how you want to describe them. It's a much simpler, much lighter arc. Fortunately, in the spot we wanted it to be. So it turns out if you throw out all of your other constraints, things get easier. If only we could do that in life. When we do have breakdown because of the voltage reversal, we end up with a few features we did not expect. Namely, this is our anode. We suspect it's actually a cathode at the time. But along the metallic surface of the cathode, we evolve so much plasma and we suspect so much current that the same fractal-like description that would be applied to the insulator surface, we actually see evolve around the surface of the aluminum anode, cathode, likely cathode. A pin is an appropriate word here. The samples we had were fundamentally limited by age, and this is a stressing process. Again, we're applying huge voltages to a 6 millimeter type gap, so the electric field is massive. Means we were able to push samples to failure, and what does that look like in a physical sense? Typically, we would end up eroding a nice little pinhole somewhere along the front surface, and if we let that ride, the pinhole would grow. It would be the preferential source for energy to deposit through. That area would heat, and we would blow chunks off of the front of the insulator. Makes for really pretty pictures, but I recommend against doing it in practice. So some really basic conclusions. I see my nice countdown warnings over here. Surface flashover is a very active area of research, and cathode-initiated flashover has been a known problem for a while, but we've gotten pretty good at solving it. An anode-initiated flashover is fundamentally the limit for large machines, and we would like to understand it better in order to push into newer territory. Fundamentally, this means more energy, higher fields, more science at higher energy levels, accessing things like ICF or dynamic material studies. And with much effort, we in fact can put flashover in a spot we control. In terms of future work, the next step in this process, we would really like to move on to doing some optical deflection diagnostics, where we take a laser, shine it across the arc, and because of the composition of the plasma, we would like to see it bend back and forth, and that would let us do some estimation on the actual density and population of the neutrals and electrons in the evolving plasma.